Okay, so for everything we studied in translational physics up to now, there's going to be an equivalent in terms of rotation. So let's just look at rotational inertia. So rotational inertia is essentially the same thing as mass in translational physics, and we're going to symbolize it with the letter I, which is a little bit tricky because sometimes it looks like a one. Okay, but basically, think of it this way: just as mass is the resistance to an object's translational acceleration, I is an object's resistance to angular acceleration. Okay, so it serves the exact same thing that mass does in all the physics we've done up to now. So it's a little bit different though, and I should point out that College Board likes to ask questions about the this relationship between the mass and the radius that's associated with the value for I, rotational inertia. But the good news is it's really not that challenging. So let's just go through this. So what we're going to find is this: the rotational inertia I of an object or a system is going to be directly proportional to the mass of the system. Double the mass, you double the rotational inertia. And it's also going to be directly proportional to the square of the radius. In other words, the distance between the mass and the axis of rotation of the system. So that we have a direct proportion to mass and a direct proportion to the square of radius. So let's take a look at this here. Okay, so let's just say here's my axis of rotation. I have two masses that are both a distance r away. Okay, so here the value is just going to be I. All right, but now if I double the masses, now that the mass of the system is doubled, but the distance between the mass and the axis of rotation hasn't changed. So I find that the I value has now gone up by a factor of two. In other words, I is directly proportional to the mass of the system. We went from 2m to 4m. Okay. The more distance there is, and this is really the thing they're going to hit you with on the test, the more distance there is between the mass and the axis of rotation, r to 2r, the harder it is for the object to accelerate. Okay, and we'll look at that in class. You'll see, like, we have some good ways of making that very intuitive for you. But in this case, I left the mass the same. So I have 2m and I have 2m, right? M. But in this case, I went from r to 2r. So basically, the mass is now twice as far away from the axis of rotation it was before. And what we'll find is it is 4 times harder to cause this system to have an angular acceleration. So the idea is then we can combine this, and this is how we define uh, the I value or the rotational inertia of a system, which you'll notice sometimes they'll refer to as moment of inertia. That's sort of an older way of referring to it. But if you look it up online, which I know a lot of you'll do, you're going to see references to moment of inertia. It just means the same thing. Okay. So the rotational inertia is simply the sum of the mr squares, where r is the distance between the mass and the axis of rotation, and m is the mass of the object. Okay, so let's just take a look at a few systems and see how this plays out. And these are the types of questions. So please take notes, pay attention. These are the kind of questions the College Board is going to ask you. Okay, so here I've got a system together where I have an object of mass m that's a distance r away from the axis of rotation. So let's just say this is going to rotate in a counterclockwise fashion. So I have an object of mass m that's distance r away. So I have mr squared for that. I have an object of 2m a distance r away. So now I'm going to have to add that to the system. So that's going to be 2m times r squared. And now look at this one here. It's a mass of m, but it's 2r's away. So that's 2r squared, right? So 2r squared, that's 4mr squared, plus 2mr squared, that's 6 plus 1 over that. So it's 7mr squared. So those are the kind of assessments of the situation you're going to have to make at some point on the test to show that you understand that it's the sum of the mr squares. But now look at this. They will often be asked, well, what if we move the axis of rotation? So this is no longer the axis of rotation. So instead of this going around this way in the plane of the screen, now this is my axis of rotation. It's passing through these two objects and now is rotating in and out of the screen. So really, these ones are remaining stationary essentially, and these ones, and this one in mass is coming in and out of the screen. Now, in reality, these objects do have rotational inertia, even if they're not moving, in a circle, right? But we're going to ignore that in these types of problems. So we treat them as point masses for these types of problems, right? So that means all I have in the system is one object of m, and it's a distance 2r away. So in this case, the rotational inertia, if I make the system rotate this way, is 4 mr. Remember, before, when I went this way, it was 7 mr squared. Now it's just 4 mr squared. Let's move the axis of rotation to somewhere else. Let's put it down here now. Now, what we're going to see is this. The farther the mass, the more mass there is, and the farther that mass is from the axis of rotation, the greater I was about to say moment of inertia, but I could say the greater the rotational inertia is going to be. Okay, so in this case here, I have basically this object is going to remain stationary, and these two objects are going to rotate in and out of the plane of the screen that you're looking at. So this one I basically treat as being 0. So now I have m, that's a distance 2r away. So I have m times 2r squared plus 2m, that's 2r away. So that's 2m 2r squared. So when I do the sum of my mr squares, I get 12 mr squared. So you see where that axis of rotation is makes a big difference in what the rotational inertia of the system is going to be. And so there's usually going to be some question on the test where they ask you to evaluate the different uh, rotational inertias. Often they'll ask you what would be the maximum or the minimum. You have to think about moving that axis to different places. Now, there's one that's kind of important to think about. So if you take like a stick that has a mass on either end of it, like it has 2m on one end and m on the other one, and you throw it in the air, you'll notice it's going to rotate around its center of mass. That's going to be its axis of rotation. And let's just see why. Okay, so let's just do this. I have the system. It's just a mass of 2m. That's a distance r away from a mass of m. If I make this my axis of rotation, then this one I can treat as 0. So then what I have is just mr squared. On the other hand, take the same system and make this the axis of rotation. Now this one's not going anywhere, so I treat that as 0. So now I've got 2mr squared. So you can see there's a big shift in the rotational inertia depending on where I put that axis of rotation. Well, what's the minimum axis? What is the minimum value that I can get for this system if I keep the axis of rotation within the plane of this screen? Okay, and what we're going to find is, well, if I keep it vertically in the plane of the screen, let's just try that. Okay, so the answer is going to be the center of mass. Watch. Okay, so now I'm going to put so if I have 2m here and m here, then that means the center of mass is going to be 1/3 of the way between these two. Is going to be 1/3 away from the 2m and 2/3 away from the 1m. Okay, so that you could do the math. That's what you're going to find. Okay. So therefore, let's just do some of our mr squares. I have 2m times 1/3 r squared plus m times 2/3 r squared. So that means I have 2/9 mr squared plus 4/9 mr squared. I have 2/3 mr squared. Now remember, when I put it here, it was mr squared. This is a third less than that. This is the minimum I can get, which is why it's going to rotate around that. Now, perhaps you could look and say, I see a way to make the mr squares 0, and that is if I pass the axis of rotation this way. And if these are point masses, that would be true. But now we've got to step up a little bit and go, all right, well, there's really no such thing as point masses. Keep in mind, the physics problems are going to give you on the test, they'll say treat as a point mass. But otherwise, let's try this. What if I have, geometric objects, say, in this case, spheres? Well, what you need to know, that the big takeaway and the thing they're going to really test you on when it comes to rotational inertia is simply this. The farther the mass is distributed from the axis of rotation, the greater the moment of inertia, because the relationship is mr squared. So when you move that mass away from the axis of rotation, you are going to greatly impact the rotational inertia of the object. So let's just look at the case of a hollow sphere and a solid sphere. Now, I want to say right up front, I'm going to say it several times in the screencast, you are explicitly not supposed to have memorized the values for the rotational inertia of, say, a hollow sphere versus a solid sphere. They will give you that. So if you have a problem where that's going to be necessary, like an FRQ, they will say it's a hollow sphere and the rotational inertia is going to be 2/3 mr squared. Okay, so you don't have to memorize this. Don't, okay? But here you go. So here's the idea. In a solid sphere, the mass is distributed farther away from the axis of rotation. And so what I find is the hollow sphere has an I value of 2/3 mr squared. But if it's solid, that means a lot of this mass that was way out here on the shell is now in closer. So that's going to make more of the mass closer to the axis of rotation. It's going to reduce the rotational inertia. So rather than getting 2/3 mr squared, I get 2/5 mr squared. So we see it's got less rotational inertia because the mass is closer to the axis of rotation. You get that in your head and you'll do fine on these problems. So the objects we often have are balls, which are spheres, either hollow or solid, or discs versus hoops. And we'll look at these in class too. So if I have a hoop, again, it's like a solid sphere. It's like a cross section of a solid sphere, right? So it's all the mass is distributed on the outside of this hoop. So basically, if this is the axis of rotation, well, this mass is all the same distance away. So it's just mr squared. But if there's a disk, then a lot of that mass is distributed closer to the axis of rotation. So it turns out it works out to be 1/2 mr squared. And if you were taking calculus-based physics, this is one of the things they have you do. They have you, take an equation and demonstrate why you would get these two different values. But this isn't calculus-based, so you don't have to. You don't even have to memorize this. Okay, let's keep going here. So again, you don't have to memorize them, but you'll have reference sheets in this unit when we work. So basically, you have a hoop and a cylinder. You can have a bar that's rotating around its axis this way or around its in this way. Now you notice here, it's going to be 1/12 because I'm passing it through the center of mass. Here, I'm not at the center of mass, so it should be greater, and it's 1/3. Again, you don't need to memorize these. Okay, so what do we do with all this? Well, why do we learn about mass before? One thing that mass is important is it provides inertia. Inertia is resistance to acceleration, and it's overcome with force. Okay, and so what we have now is torque. Remember, is just force. Is the rotational equivalent of force? So we're going to say, just as Newton's second law is F equals ma, Newton's second law of rotation says torque is equal to I alpha. And that's the thing about this unit, guys, is that whatever the unit is in translational physics, you can just replace it with the rotational one, and it's the same relationships. Force, the rotational equivalent is torque. Mass, the rotational equivalent is I, or rotational inertia. A, and the rotational equivalent is alpha, which is angular acceleration in radians per second squared. So we can basically apply Newton's second law the same way we did before, except with objects that are rotating rather than going from point A to point B. So let's take a look at this. It took me a while to draw this. I'm kind of proud of this. So what I've got here is I've got this disc, a solid disc that has a mass of 4 kilograms. So let's look at it from a side view. I have an axle, which is shown here, this black dot. There's an axle, frictionless axle, that passes through this with a very minimal dimension. All right. And the radius of this solid disc is 0.4 meters. And I've attached to it a very small, very light, uh, basically I can ignore the effect that this added part has on the angular, uh, the rotational inertia of the system. But I have this other disk attached to it here that has a radius of 0.2 meters. And the reason it's attached to it, so when I look at it from the front view, here's the 0.4 meter 4 kilogram disk. Here's the 0.2 kilogram very light disk that's been glued onto it. And the reason is I've got a string wrapped around the smaller one, and I've got a mass hang on it that's producing a tension force of 16 newtons. This is a pretty common setup for these problems. So let's just get used to looking at these. And in our next lesson, we'll look at lots of variations of this. But here you go. So a force of 16 newtons, a tension force, is applied to the 0.2 meter part of the system on a 4 kilogram disk with a radius of 0.4 meters. And what we want to know is, what is the angular acceleration of the disk going to be? And how long will it take this mass to fall 2 meters to the floor? I put that in there because I want you to be able to toggle between angular motion and translational motion. Let's give it a try. Okay, I want to find the angular acceleration of the disk. Okay, so that means I'm going to use Newton's second law of rotation. Right, so that's what we often call it, Newton's second law of rotation, just Newton's second law. So that's going to be torque is equal to rotational inertia times angular acceleration. So what is the torque? Well, in this case, I have 16. Remember, torque is equal to force times radius times sine theta. But because this on a system like this, it's always going to be acting at a right angle to it. Sine of 90 is 1. So I just get 16 times 0.2. That's the torque. Now, this is a solid disk, so I look at my sheet. Oh, yeah, solid disk. If it's a solid disk, is 1/2 mr squared. So I have 1/2. Here's the mass, 4 kilograms. The radius of the disk is 0.4 meters. and I'm solving for alpha. So when I solve this for alpha, I get 10 radians per second squared. It's just Newton's second law, except I'm doing it with something that's going this way instead of something that's going that way. All right. But now I want to know, how long is it going to take this disk to this mass to fall to the floor in this case? All right, let's see what we got here. All right. So here's what I know. I know that this object is accelerating, but its acceleration right now is expressed in terms of angular acceleration, right? So I know its angular acceleration is 10 radians per second. So what I've got to remember is, remember, for every uh, uh, angular value, rotational value, if I multiply it by r, at least for displacement, velocity, and acceleration, if you multiply it by r, you get the translational equivalent. So alpha times r equals a. Alpha is 10 radians per second squared. Now I got to be careful. The radius of this part of the system that's attached to the string is 0.2 meters. So that means 10 times 0.2 gives me a translational acceleration of 2 meters per second squared. So now I know how fast this is accelerating towards the ground. All right. And so what I can do then is I can say, all right, well, therefore, I've got I'm going to use delta x equals 1 half at squared to solve this. There it is again. We use it so much. Okay. So if the distance is 2 and the acceleration is 2, then 2 times 1 half 2 times t squared, the time is going to be root 2 seconds. Okay. So I won't lie to you. There are some questions we'll get with Newton's second law of rotation that are going to be quite challenging. We'll look at those in our next screencast. But for right now, you got to admit, it's pretty straightforward. All right. So thanks for watching this. I think this is kind of cool. Hopefully you do too.